Good afternoon, everyone, and a warm welcome to yet another online learning venture as a part of Astronomy Bootcamp 2024. During this 21st of the June till 21st of the July, we'll be having several different topics for discussing about the various astronomical developments and also various research projects. As today's morning, you have done hands-on with Dr. Chiranjeev Kunar, and now we are here. We kept it online because most of the students are not from Delhi NCR, and probably they are not uh, available to come offline with the session. So we tried to make some of the session online available to them. So we've been using this YouTube live so that students sitting across the border can also get benefited of some of the topic which we are discussing during this boot camp. So Planetarium is privileged and honored and also thankful to Dr. Anand Ahota for giving his time to discuss more about the extragalactical radio astronomy through citizen science. So probably I really hope and urge you to ask as many questions, and also sir will be sharing during the presentation like how you can also be part of such citizen science project in which you can also devote your time and devote your learning and also get something in return as a part of like knowledge. So with this, I open-heartedly welcome Dr. Anand Hota. He's PhD. If I talk about Sir's present association, currently he is UGC Assistant Professor at UMDAD Center for Excellence in Basic Science, CBC University in Mumbai, Delhi, India. UGC Central University Grant Commission, Ministry of Education, Government of India, Director and Principal Investigator, RAD at Astronomy, RAD at Home Astronomy Collaboratory, India, member International Astronomical Union, IAU Paris, Astronomical Society of India, ASI India, SKA India. And also he's running this rad at astronomy. In past also we have done rad astronomy workshop with sir. Now I request Dr. Anand Hota sir to please if you can just open the mic, because this session will be like students who are sitting offline at the planetarium, they're also attending it. Soon you can see them via the webcam, and also most of them are already joined via YouTube live. So probably in both way we'll try to take questions in whatever medium, like offline also in this hybrid mode.
Okay. Good afternoon, everybody. Thank you very much, Karuna ji. I really feel happy to come back because the RAD workshops in planetarium is very, very old. Since the days of Ratnasri ji, we have been engaging people and training them. So it is always a pleasant feeling to come back to the same spot, but keep training new and new students there. So uh, I cannot see all of you, and I'm not sure that it will be YouTube live and how many are watching, but doesn't matter. All of our who are interested in learning something are students. So anybody interested can come. As in there at home, we say that ABCD research means any BSc, BE, BTech, anybody can learn. So I'm usually a very interactive person, uh, but because of the online nature, I will use Google's Jamboard to draw something, and I don't know if you are allowed. You can stop and ask questions because it is short time. Unless you feel free and analyze the information that I speak or so, good questions will not come out. If good questions actually come out, then only you are actually truly processing the information that you are getting. So that way, I will of course start a slideshow, speak few things from there, but at the same time I will go back to blackboard kind of thing so that you understand the concept. It will not become a purely slideshow speaking. Okay. You can get pure slideshow talks from very famous persons, famous astronomers in the YouTube. So what is the extra benefit of having somebody from your own nation and speaking to you interactively? This is the blackboard work and question and answer sessions. Okay, so let me start sharing my screen. We straight away go to some organized way of speaking something. So the screen, entire screen. Somebody just tell me if you can see my screen. Somebody speak.
Yes, sir. We can see.
Okay, great. So here you are in the boot camp. Uh, it is something similar. Camp is that you put a lot of people, and in an interactive way, you learn some skill. It is not just a recorded video that you are listening. If you have been given this thing, I had put the title of my presentation or session and the abstract. Title: Extragalactic Radio Astronomy through Citizen Science Research. What is extragalactic? We are living inside the Milky Way galaxy. Anything that is beyond, outside this Milky Way galaxy story, that is extragalactic. Radio astronomy, the astronomy that you do by looking at the any heavenly object that is primarily giving radiation in radio band, that is radio astronomy. Primarily, things that you see in the sky or the night sky, historically it has been dominated by optical band emission. So we are kind of biased towards what we see in optical band. For example, stars, nebulosity, planets, Sun and Milky Way, dust obscuration from them. But what you would see in a radio band can be entirely different, very, very different. The radio telescopes that we use, their sensitivity does not listen to the law that the star's radiation follow. So what is bright in the optical band, like stars, need not be bright in the radio band. There are various radiation mechanisms through which different kind of radiation comes up. So some kind of physical processes give more radiation in X-ray, some give more radiation in optical, some give more radiation in radio. It's a physical process that defines where the maximum of the energy will be radiated at. So we'll be focusing on radio band. And second half, citizen science research. What is this citizen science research? In this internet era, you must have been knowing this, but this is slightly different from what people used to call amateur astronomy. It's somewhat similar, but it's not exactly the same. What you do, amateur astronomy mostly, is that you go to amateur astronomy clubs, go for a stargazing, you have beautiful experience. The feeling of observing the night sky is entirely different when you go to a hilltop, the mountain top, and in the night you observe the stars. That is not comparable in any other way, sitting in the laptop or in the auditorium and learning something. The feeling of a planetarium, trying to mimic that, is certainly not the same as watching the same beautiful images from Hubble or anything on a laptop screen. So the feeling and experiencing, it has all gone to how seriously what are the different modes of learning. I'm also one of the person who was inspired by looking at the meteor shower, looking at the scene in the scene in the planetarium, looking at every day coming to the news, 9 o'clock around, and watching the Sumet or Levy 9 comet falling on Jupiter. You should watch this video in YouTube. So, so those people who used to night sky and observe through a small telescope and get used to astronomy, they're amateur astronomer. It is not their profession; they won't get paid for that. It is our amateur activity, passion. Today, what has happened? is that your information about the sky is not limited to planetarium or books, but now you are enriched by YouTube videos, by newsletter, by online books, online courses, and you are so much enriched by the information that it is crossing the limit, crossing the education, outreach, and almost reaching to the research. What is coming to research like? That can you look at the images, look at the spectrum, look at through a telescope, that you can find some new information that the astronomers do not know about. You are contributing new knowledge that has become research. So the telescopes, current day telescopes, are providing so much of data recorded or analyzed through partially analyzed through computer that they are ready to use, ready to analyze, ready to interpret for by even common man or common student. And in return, they can classify galaxies, they can understand, they can find something exotic and report back to the astronomers, to the telescope, to the observatories. That can be entirely new, nobody has seen before. And that form of amateur level, outreach level, interaction that crosses the education and reaches contributing new knowledge, that is citizen science. So as I have written here, all of you, most of you will be students, I can guess. I do not know, I am not seeing your faces, I do not know about your details. But now you know that reading from classroom is not sufficient to get selected to a research internship process. Everybody tries to do some kind of project. And the teachers in your colleges or universities cannot provide number of projects similar to the number of students they are teaching. So you need to look for projects elsewhere. The number of scientists are not exactly same as the number of students. So you have to compete. So if you want to compete, how do you show yourself your CV to be better than the others? How do you stand out? You have to do a project. Physically traveling somewhere and doing a project is costly and requires a lot of effort, but online project doing, or in some way similar to citizen science research, is easier. That is why during your BSc MSc process, if you can take part not only in lecture, workshop, but also in some small amount of research activity, through citizen science research it may be, your CV will stand out. You have better chance of entering research internship or doing MS or doing PhD. So, as I said in the beginning, my talk will be slightly different. Different in the sense, it is not going to be presenting images and speak about the images. I will try so that you can understand those images. Images or photographs are not actually just to appreciate its structure and its color. It is something to be understood. Images are not to be appreciated and um, about its structure and color only, but you have to be amazed and try to understand what is the quantitative expression, what is the physical parameter that the image is showing you. Okay, for example, in the screen, wherever you see this part is looking red. Why? This part, some parts are looking white, some parts are looking bluish. Why? Why the sky is depicted here pure black? So anything that you see can be actually analyzed. Although it is combination of 3-4 images, I know, but still each part is true to its observation. Okay, so we will focus on how do we take a imaging data and how do you understand it, how quickly you can go to multi-wavelength images of galaxies and then contribute to or start learning interpretation so that the moment you are given a high resolution, high sensitivity new image, you are ready to find something new. Because at that sensitivity level, at that resolution level, at that wavelength, most astronomer has not seen that interesting thing. You may be the first person to notice the scientific importance of it. So That way, we will start looking at galaxy images and multiple wavelengths. Most of you know how to look at how to understand HST images looking very pretty, even James Webb telescope images now. Some objects will be looking blue, some will be yellowish, some will be green, or some will be, say, reddish. What does it mean? Some are point sources, some are extended sources, some are curved, some are cloud-like thing, fuzzy, some are exact, well-defined shape. What does it mean? So we will understand these slight differences to know those jargons, know these concepts that will identify what is important scientifically. I give this standard example everywhere that suppose if I tell you that you spot gold, how do you know what is gold? Where is gold? Few characteristics everybody knows. It looks yellow, it looks shining, it's a metal. Oh, but there can be a brass-like thing which may be mimicking gold. Yes, that is absolutely what you are looking for, exactly the precious one. There may be something which looks similar, which is not that precious. To understand the what is important is the first step. If you're walking on the road, if you say that I discovered a green leaf, nobody will believe. If you say that I discovered a red looking leaf, it is not cut in the middle, it is naturally like a ring, then it is interesting. How did the leaf develop a structure which is not some kind of circular, some kind of petals, but it is a ring-like thing? So if you find something odd, that is where the research actually starts. Each has to. How to find something odd? Structurally and color-wise, if I can define that interesting thing in a simple language, you can spot it. If I give you the most powerful telescope's images, the chance of discovery increases. That is how citizen science projects are defined. Simple, but quality of the data increases the chance of making a discovery. And astronomers will then, or scientists will then follow it up, and you can get authorship for your, or the due credit for your contributing to the discovery process. So, in the process that I will be describing, if you can find something, maybe tomorrow or day after, or some other time when you come back, you are prepared to do some discovery and get authorship in some important discoveries that you can do. Okay, so it is my affiliation, my name did not go. In various institutes since last 11 years, we used to conduct these discovery camps and astronomy workshops, like I previously said, in Nehru Planetarium also there. So I will not go there. You look for in Google one of the latest discovery from the Red-Home Collaboratory, Red 12. Red-Home Citizen Science discovers a monster black hole spewing fire at another galaxy. What it means is a galaxy. This is also yellow color galaxy, false color unit of course, elliptical galaxy, elliptical galaxy. What you see the red and the blue color part is the radio telescope image. Radio telescope does not see the galaxy, the optical telescope does not see the radio plasma. So naturally we are going to learn this kind of making overlays of multi-wavelength data. This made it was similar as letter publication, very important finding, a short paper but important paper, and it has used GMRT, our own Indian telescope data. It has used optical telescope data, another radio telescope data from South Africa. GMRT is India, this is South Africa, this is Canada, France, Hawaii telescope. So multiple countries involved. The 22 paper. Okay, this is the title of the paper that you can see. There are few professional astronomers, few amateur astronomers. You already must be knowing Megha Rajuria. Avinash Kumar also gave a talk to you. So these people have contributed to discoveries at the citizen science level. I will show the simulation of that. It's an animation or artist impression inspired by real physics understanding. Two galaxies, they themselves are rotating, but they are going around their common center of mass during their merger, and one galaxy shoots out a plasma jet that bounces from the other galaxy and forms a bubble. It is based on the previous direct image. It is animated picture. to make you easily understand. Okay, so this I have already described that locally you may be having limitations of the resources in your colleges and universities, small telescope, only educational. Globally, you are always passionately interested about the big things, the first image of black hole or Higgs boson discovery, that kind of thing. What is there to bridge you at the resource poor educational institutions to the scientific aim that you all are having, big dreams, is through this kind of a citizen science collaboration process. Then you can quickly join a big project, not exactly this, but bigger telescope project, and contribute beyond your education to research. Okay, so there are plenty of institutions that support it at home, and just like Planetarium is hosting this, mm, so we will go directly to the concept. Okay, this kind of thing that there are in the red 12 discovery I showed you optical galaxy from which a plasma jet comes out and hits another galaxy. Here is a animation, not animation but simulation. Simulation is mathematically physically driven process. For example, creating the way universe expanded in 13 billion years, say you create that in the computer that it expands in 13 minutes. You are recreating that thing. So here, for example, the center of the galaxy, there will be supermassive black hole, matter falling into it. From there, the magnetic field line, which is white lines here and there, that is strong, and the particles are gyrating around the magnetic field lines and trying to flow outward. That is what is radio jet. So the moment you look at a active galaxy where the black hole is accreting matter, there is a 10% chance that it can create a radio jet. So the radio jet will be giving radio radiation dominantly, and the optical galaxy will be at the center. So our GMRT is going to see in this kind of imaging this kind of plasma lobes, the emission blobs, either side of the optical galaxy. I don't know, but Chiranjeev may have described these things while giving. I don't know how basic or how far he could go. So that is what we will be actually looking at in future, very soon. Okay. So before you go there, the radio or telescope image, here is one of the very basic concepts that we need to understand. Okay. So you have all read this thing, Wien's displacement law. What is Wien's displacement law? That the wavelength at which an object is radiating maximum amount of energy, the peak at which the emission is radiated, and the temperature of the object at surface, to multiply them, it will be a constant. That means if the wavelength is long, very long wavelength, I am giving the example. Suppose this is a hot iron rod. This part is looking yellowish. This is actually hotter than the part which is looking red. This part which is not looking red, not looking yellow, optical light is not visible, it may still be hot. You can guess it is connected. So at what wavelength it is radiating? Longer than the red. So infrared. Peak emission is infrared, peak here is red, peak here is yellow. Here you can see the same thing. That yellow regions are hotter, red regions are little cooler, still radiating optical, and this can go to infrared beyond that. The star's color that you all know, different stars are giving different light, different color. There is nothing but the surface temperature of those stars are different. Blue stars are hotter than the red stars. So if you go that way, so So different color of stars simply means that they are sophisticated different. A galaxy is not made up of one star. How many stars our Milky Way galaxy? Say 100 million stars. Okay, 100 billion stars. So not all star will be sun-like star. There will be several millions of M-type star, several millions of this type star, millions of this type star. That way it becomes 100 billion. Some billion here, less than a billion here, close to a billion here. So there is a distribution. There is a mass distribution you can call. So the light that they give is ultimately a result of that. Suppose all the stars were only O-type stars, 100 billion stars, the galaxy will be looking entirely blue. Suppose all these 100 billion stars should be M-type star, the whole galaxy will look red, but it is not. So it is a mixed color. So which kind of star dominate in number and light output, that defines the color of the whole galaxy made up of 100 billion stars. So that is what we will go. So in radioatom, we have combined three wavelength data to go beyond optical. What is it? What we call is infrared, optical, UV. Infrared will be in red channel, optical picture will be in green channel, and ultraviolet picture in the blue channel. This kind of a combined picture. Every picture is a combined picture. The color picture that you see in your mobile phone is nothing but three different pixel pictures: red, green, blue. So similarly, so a galaxy will be looking colorful through this false color picture, or called RGB images. Infrared, optical, UV, IOU image. So the region of the galaxy which is bright in UV, taken from galaxy ultraviolet telescope data, there is a lot of radiation coming in ultraviolet band. That is why that part will be looking blue in this RGB picture. The region of the galaxy that will be looking red will be bright in infrared, so there are a lot of cold stars, dust, EH, etc., etc. That is why that part will be looking bright in red. In between, green will be bright. Similarly, we will also have one more variety of picture, similar RGB picture. Here, again, radio, optical, radio. Red will be one radio picture, green will be the optical picture, and blue will be again a radio picture. Following the same convention, red will be long wavelength picture at 150 MHz from our GMRT, or 2-meter wavelength picture, and blue will be from a VLA telescope in USA. Its wavelength will be 20 centimeter or 1400 MHz. So in such a picture, the galaxies will be looking red, green, blue. Green is optical, red is Indian, blue is American. So red looking region will be giving more radiation in 150 MHz here. Did I write the frequency? Sorry, I didn't write. Somewhere else. So 150 MHz 2-meter wavelength, and blue looking region will be 20 centimeter bright. Very similar to what we described here. This kind of two varieties of RGB images, if you can understand a lot. Your journey in multi-wavelength extragalactic astronomy is started, if you can understand these two things. So we'll practice these two images, many galaxies. Each one of you will be making different galaxy images. We'll discuss them. So here is the tool. I will give you the link in the description, in the chat message also. It is simply a RGB image maker tool in our website, radioatomindia.org/RGB maker. What you will put? You will put your name and a galaxy name that you know, M31, M81, M83, whatever, NGC 37, NGC 3419, NGC 307, anything that you know. I will just define those things soon. And a default size in the sky has been given. It is 0.12 degree. What is a 0.12 degree? Our sun and earth are half a degree. Okay, so there are a lot of galaxies or stars in that part of the sky. When the moon comes up, behind the moon there are so many stars that we do not know what else it is blocking. So here, for example, we are assigning how big part of the sky the RGB maker tool is going to return to us. You can change it, leave it default for the moment. If the galaxy is filling up, is overflowing, you increase the image size, see a bigger part of the sky. If it is too small, you can decrease it. And here, by default, it is IOU ROR image tool return tool. Infrared, optical UV, radio, optical radio. So which galaxy you will be analyzing? So it has been defined in a certain simple rule. NGC is the prefix, XYZ will be the number. NGC 1, 2, 3, NGC 4, 5, 7, whatever it can. So what is, suppose your last three digits of your PIN code is XYZ, to make an image of NGC 1 XYZ, NGC 2 XYZ, up to NGC 7 XYZ. You have many galaxies in your assigned list to make a galaxy image. Understand now that you will be making a RGB image of a galaxy NGC 1, 2, 3, NGC 4, 5, 6, NGC, etc. etc. Depending on the last three digits of your PIN code, you can put NGC, suppose your last three digits NGC XYZ, then NGC XYZ, NGC 1 XYZ, NGC 2 XYZ, up to NGC 7 XYZ, many galaxy images you can make. Whichever looks pretty, whichever looks resourceful or informationful, that we will be discussing. Okay. So, for example, see this picture. Suppose I put the, the Orion constant. This is plates or kritika. Sorry, I was saying Orion. If I make a IOU picture, what is that? Infrared optical UV picture. Infrared 22 micron image is showing this nebulosity bright, giving a lot of radiation in infrared. Optical, green part, UV, blue part in this picture. Additionally, I have put actually GMRT images contour in the white lines drawing that you see. We'll come to that soon. So in this picture, you are getting the information that there are stars. Yes, there are 5 stars here. There are many other stars also. But there is a fuzzy part which is brighter in infrared, more brighter than optical and UV. What does it mean? That this part of this cloudy thing, fuzzy thing, is such an object that it is giving more radiation in infrared compared to optical and UV. Because this cloud is actually cold stuff, very cold, not red hot, but cooler than the optical light emitting temperature. If it is 100 degree, 200 degree Kelvin, the peak of the emission will come in the infrared. That is how this is bright in 22 micron or 12 micron band, not that bright in optical. This is not hot, not burning, not glowing like a star. Some amount of light only scattered by the light from the stars. Okay. Similarly, see this picture, the same constellation. What I have shown here is now ROR picture, radio, optical, radio picture. And 41 plates or kritika, the same stars seen in optical, but the stars are not seen in radio band. Neither blue, not red band, not GMRT telescope, Indian telescope, not in ultraviolet, not in VLA, American telescope, which radiates anything. The process is not thermally heated star-like object. The process is very different that gives a lot of radio radiation. So what are these red and blue blobs or contour drawn blobs? These are the background galaxies from where the plasma lobes are coming out from the accreting blackholes. So the bright stars that you can see in naked eye is not visible to the largest radio telescopes, because these telescopes are sensing radio band and some other physical process other than the stars are giving more radiation. So, as I said in the beginning, the radio astronomy is going to see very different things than what the optical astronomy mostly sees. The radio sky is full of plasma outflows from the black holes far, far away than the stars which are very near to us. Okay, so here, for example, we are looking at extragalactic. I will not discuss stellar things or galactic things. This is so-called sombrero galaxy. Left hand side is an optical picture. Optical light is coming from the central part, bulge part, and on the foreground there is a dust disk, dust ring that is blocking the light from the center. That is why you see a darker patch, dust silhouette, dust flame, dust ring. So the optical light, few thousand angstrom, is being blocked by few micron size or bigger dust particles. It cannot pass through them, bigger than the wavelength itself. But that ultraviolet optical light which is being absorbed by the dust, after absorption of these photons, what will happen? It disturbs the electron going around the nucleus. It shakes them, it increases their energy level, it heats up the matter, and the whole dust particle actually is getting heated up. The heated up dust is radiating like a black body. And heated up dust is radiating like a black body. Depending on the temperature of the dust, it will give a black body radiation in all wavelength, but the peak will be according to lambda max T Wien's displacement law. So what is happening in there? If you see this galaxy in optical, you see a dust lane. But if you see this galaxy in infrared, 3 micron, 5 micron, 12 micron, 50 micron, that kind of thing, from infrared 3-band picture, if you make a picture, the dust ring from the back side as well as from the front side can be seen radiating in the 22 micron. Here it is silhouette, here it is in emission. The dust ring can be seen in emission. Here is the optical picture. This is pure infrared picture. 3-band also you can put. Similarly, this galaxy, the largest spiral galaxy, what you see here is an IOU picture. Infrared, optical, UV. What you see, the central part of the bulge or the bar part of the galaxy is seen green. Middle part is seen red, here as well as here. The further away spiral arcs are seen blue. What does it mean? It means this part is brighter, relatively more bright in ultraviolet. Why? Because there is more number of O and B type stars which are massive and young and hot. According to lambda max T constant, they are hotter, so their wavelength peaks. The wavelength at which they emit maximum amount of light is in ultraviolet. So according to the color code, that part will be looking blue. The part of the galaxy that doesn't emit much infrared, doesn't emit much ultraviolet, that will be looking green. The part of the galaxy, in between part, intermediate radial region, there is something that is bright in 22 micron, very cold. Why this is cold? If this part is hot stars, young stars, hot and young stars, why this is cold? Why this is sun-like stars, billions of year old stars? Why this is colder than? It is not cold. Actually, it is absorbing the ultraviolet light and re-emitting. The dust is absorbing ultraviolet and re-emitting infrared. Infrared could pass through the gas and dust, but the optical and UV cannot pass through. That is why you could see the inside radiation of the star forming region in this spiral arc. So this is billions of year old star, optically bright, dust and pH heated up region in the infrared, and young, very young, hot, massive O and B type stars are here in the end of the spiral arc. There is not much gas here to absorb. When there is lot of gas and dust to absorb that UV light, it becomes red. Because the UV and optical is being reprocessed and coming out in infrared. So I will give you one more galaxy example. This is an A, center of a elliptical galaxy, which is a Dostalian wave, IOU picture. Along with that IOU picture, I have put contours from our radio telescope GMRT, TGS system. What do you see? Young stars, dust layer, bright in infrared, and the old star of the elliptical galaxy. But beyond that, there is some plasma giving only radio. It is not giving optical light. Galaxy's optical light is over by here. There is a blob of plasma emission here, blob of plasma emission here. So that is what is a linear structure. Plasma that comes out from the center by because of black hole accretion process. The plasma goes farther away from the optical galaxy, stars of the galaxy. That is called a radio galaxy. Radio jet heavy galaxy. So the moment we look at sky with our GMRT's TGSS survey method at 150 megahertz, low 2-meter wavelength sky, it is full of this kind of active black holes creating plasma jets and lobes, not the stars. Okay, so this is another pretty looking example. The optical galaxy will be the center, plasma blobs will be on either side. Red is the Indian GMRT image, blue is the American VLA image. So from the optical galaxy in the middle looking green, pink looking blobs will be on either side. They come out as a linear jet and forms a lobe. This is a typical radio galaxy image. So once we know how a typical radio galaxy looks like in the GMRT data or in the ROR optical radio RGB image, you can now identify any source in the sky that is not looking standard. That is not looking standard radio galaxy type, but odd one, or not a well structured, but a diffuse and fuzzy thing. Say, for example, these are the roughly the 6 classes of radio galaxy. In the pure radio picture, a galaxy can be bright on either side, and optical galaxy can be in the center. A galaxy can be here and a tail extends. A galaxy can be in the middle and X-like thing. A galaxy can be in the middle and a faint tail comes out on either side. A galaxy can be in the middle, but a tail like a train trails behind. And this is one in the middle, and there are 2 blobs, one blob here, one blob there, 4 blobs. So these are standard radio galaxy morphologies. How they happen, we will discuss some other time, maybe tomorrow. So when a radio source in the sky does not fall into these 6 classes, they are oddballs. They are strange objects. And if you can spot a strange object that does not fall into the 6 classes, there is a chance that it is a new interesting source. If they are very faint and diffuse, there is also possible that one of these kind of sources have died, stopped creating jet, and the plasma is just dispersing in all directions. That is how it is faint and irregular shape, not falling into the 6 classes. So a faint fuzzy object as well as anything not falling into the 6 classes are potential new discoveries from the data that we will be looking at from tomorrow in FITS file formats. Okay, this is how the RGB ROR pictures looks like. We will come back to that later on. So, kind of 40 minutes gone. Here, I will quickly touch one more point, that when you, let me first touch here. Here you can see that the red emission pixels are bright here, faint here, bright here, faint here. So these kind of structures where the radio emission is bright, far away from the center, here the edges will be bright compared to the center. This kind of galaxies will be called edge brightened galaxy or FR2 type galaxy. For example, like this. This is bright here, faint here, bright here, faint in the middle. So edge brightened galaxies, FR2 type. Here, this is bright near the center and faint further away. This is as a darkened galaxy for one time. So this is which type? This is as darkened. This is FR1 type, bright at the center. Along with this pixel image, there are white lines. Contour image it is called. So where it is bright from outside to in, you will encounter many contours. This faint from outside to in, you are encountering only one contour. If you remove the blue and red from this picture, even the lines can be good enough to tell, once you know how to interpret contour images, that where the radio emission is bright. It's like isobaric contour, iso-intensity contour. These are the radio images are shown in kind of contour image where the outermost contour is fainter and the innermost contour is the brightest region of the image. Okay. Similarly, see here the bright and this is faint tail going. Optical galaxies can be all around. One galaxy is created this thing and the tail comes out this way. Here again, jet comes out, but the galaxy moves upward, so the plasma trail is actually trailing behind. This kind of object, wide-angle tail galaxy, this kind of object will be called head tail galaxy. See here, this is looking like X, so this is the X-shaped galaxy. It is one pair, small bright contours. Here the faint diffuse emission. This is an older episode of the plasma outflow. This younger episode that we will come to discussion tomorrow again. So what are we learning here? We are learning to understand multi-wavelength images, RGB false color images, UV, optical, IR, IOU RGB images, radio, optical, radio, ROR RGB image, contour images where the outermost contours are starting with the lower brightness value, innermost contour is the brightest pixels in the image. Contour image are mostly done in radio band so that a colorful RGB image along with the contour can give you the fourth information there. Just like this. IOU image is the RGB, contour is giving you fourth wavelength image. So what next? Next is, what are the pixels? What are these contours? What is their quantitative meaning? Okay, this is a slide from Wikipedia, obviously, that one Jansky is the unit of brightness of those pixels in radio band. Tomorrow we'll be looking at the FITS file of this galaxy images. There will be each pixel is a quantitative measurement. Image is like a number matrix. X, Y, position in the sky, and Z, the pixel value, is the brightness at that location. So it's a mathematics basically. It is not an image, it's a measurement. So what is one Jansky? You can read here that it is equivalent to 10 raised to 26 watts per square meter per hertz. A small frequency range of 1 unit frequency range, 1 hertz, 1 unit area, 1 square meter. How much energy is radiated per second? That is what? So it is like 10 raised to minus 26 watts per meter square per hertz. So the telescope that is imaging in radio band has done this measurement, and which part of the image, what is RA depth, what is XY value, and what is the Z value, the brightness value. So in the pixel, if you take your cursor, tomorrow we'll be doing that, the pixel value will be telling you how many millijansky, how many Jansky bright that part of the sky is. So that is why you could create a contour image also. This is say 5 millijansky per beam. This is 10 millijansky per beam. This can be 25 millijansky per beam. That is how the brightness is All the pixels with same brightness are connected with a line or iso intensity lines, and that is giving me the structure of the object. These regions are all say 15 millijansky, these regions are all say 10 millijansky, these regions are all 5 millions. This is the meaning of a contour image. Okay. So tomorrow we will open DS9 and try to understand this. That why would we start in something called 3 sigma level of contour image? Okay. So not much time today, but how do we draw contours? Where do we start? That we will discuss. Today, 10 minutes left, so I would go to discuss some questions that you might be having. And tomorrow we will discuss Russell index and 3 sigma and and luminosity and measurement of sources brightness. Okay, so I'm going back to my beginning of my slides and wait for your questions. Any question anybody has? Can I see the participants in the hall?
Yeah. Uh, Rishabh, yeah, please go ahead. Someone is posting on YouTube. If you have question, yes, please put your question in the chat box.
Somebody has put a question in the YouTube.
Yeah, we got it. Supernova inheritor. As a BSc physics students, where to exactly start with programming?
As a BSc PhD student, where to exactly start a program supernova generators. So, where to exactly start with programming? See, it is not exactly relevant to the talk that I just had, but I give you a general answer that from any online course or any workshop, anybody is giving a training on Python programming, just learn it. Learning any language will make learning the second language easier. So I think day before Avinash Kumar gave a talk on Python. I wonder if you are a participant or not. You ask him, you can ask a question. Um, Anything relevant to galaxies and black hole study, citizen science, if you ask, I can answer more detail. Okay.
The
How you use a
knowledge
black hole?
how
How
the image
image
of M87 black hole was
of black
formed.
hole was formed. Itself inspired. See, tomorrow we will discuss this more. How the image of anything is formed. If you can understand that, what is angular resolution of a radio image? If you can understand that, then you will be in a better situation to understand what is the meaning of getting a black hole's image. People have tried to image M87 before the event horizon people. What do they see in radio band? And what new thing or first time they saw different in the M87? If you go radio image of M87, hundreds of images will be there. So tomorrow, we will discuss that. And what you can extract from that ring-like image, Madhuvada image, we'll also discuss that. We'll start some calculation there. Okay, Harshvardhan. Sir, for example, in IURG image, does it mean that green represents the optical green or the complete visible spectrum? No. So we have taken one particular optical filter's image and supplied it to the green channel of the RGB image. So that green channel can be red filter of the optical band, can be green filter, can be blue filter, can be real infrared filter, anything of the optical band. So current RGB images, it is using the red filter of optical data and supplying it to the green channel. Not to confuse you, I did not use the word red filter. So it's the optical picture, blue is the ultraviolet picture, and red is the infrared picture. To be precise, 22 micron band of the infrared, not 100 micron or not 3 micron. Okay.
So one we got really very interesting question in terms of. Uh, Hello, sir. I'm Vivek from Vivek Rohila Observatory, Uttarakhand. How to build a small radio telescope?
Okay. So there are different people who are helping others to make optical radio telescope. The first question is uh, we need to be prepared little bit to see very different thing than what the optical telescope can see. So for example, if you have a radio telescope, what you will see with the smallest radio telescope is your dish antenna, Tata Sky or Apple TV or whatever. It will see the radiation coming from the satellite, artificial satellite. When the sun comes in front, you will get overwhelmed by the radio radiation from the sun. If you have a Yagi antenna and it is meteor shower time, you can listen the cracking sound for meteors falling into the sky. It is actually ionized gas trail that is reflecting FM stations radio. If you have a little bigger telescope, you can actually detect 21 centimeter atomic neutral atomic hydrogen line from our own Milky Way galaxy. So, uh, from a dish antenna, from a Yagi antenna to radio telescope data analysis coming from GMRT, it says full spectrum. And tomorrow you will learn what are the different things that you see in the radio band. So NCR is our National Center for Radio Astrophysics, Indian Institute of Astrophysics in Bangalore, Raman Research Institute. Various institutes help people to make smaller radio telescopes. I do not know about what is this Vivek Rohila Observatory, what kind of observatory you are having. But if you are having a optical observatory, you must be at a high level from the ground, and a radio telescope will be a nice place to see something from the sky, not from the city telephone communication. That is a nice place.
Piyush Sharma. Hello. What are the future advances that we can expect in the field of radio astronomy, like the new age technology and all that stuff?
Okay. There are two directions that is actually world is moving and going to see something very new. The Event Horizon Telescope is continuously in kind of upgrading itself. So they will have more capability on resolution, sensitivity, polarization capacity. So you will start seeing lot more physical details that is closer to the black hole's event horizon. That is one interesting thing. Second interesting thing is the terahertz imaging. So it is not infrared, it is not submillimeter, but terahertz. So beyond your concrete wall, what is there, 100 terahertz you can see. So a very different universe can be seen in terahertz band. Third thing, what is the biggest telescope that is coming up is square kilometer array. India is also part of it. Thousands of crores will be going to help that telescope build and function. So you will be seeing many different things that earlier GMRT or low frequency telescope has not seen. For example, if you have a magnifying glass, suddenly you have a 10,000 rupee microscope. That kind of different thing you will see altogether. What you cannot even imagine. You do not even know what are the new things that you will see there. So the square kilometer array, when it will be coming, you will be seeing things that you have never imagined. So these are three new directions I would say that the radio astronomy is going to see. Event horizon telescope, terahertz imaging, and square kilometer array.
So now we'll take one offline question. Student who are sitting at the planetarium, please introduce yourself and please ask your question.
Good afternoon, sir. I am Priyanshu Ranjan. Am I audible?
Can you
Yes.
put your volume little up of the system volume? Rishabh, can you help him?
Hello.
Yeah,
Audible properly?
Yes.
Good
yeah.
afternoon, sir. I am
Good
Priyanshu
afternoon.
Ranjan, and I want to ask that is citizen science research and amateur astronomy are they correlated, or like amateur astronomy does not involve complexities that citizen science research does?
Did not worry too much. It is only a matter of definition on whom do you talk to. There is complete overlap. There is some part that is they never had. For example, the citizen scientists do not have an instrument, do not have a telescope for their own, mostly. And if you have a telescope of your own that you can contribute, that is a different kind of citizen science. For example, citizen science, either the telescope is supplying you data that you analyze and return, or you have a telescope that you can observe and supply the data. The data can flow in both the directions. There is also a citizen science when you contribute your data. So amateur astronomers are there to learn something. Not necessarily they are going to contribute to the new research result. So they will still be called amateur astronomers because they are learning, they are having a tool. But they need not be discovering entirely new thing. But citizen scientists have to keep on doing some contribution so that it creates new knowledge. And it is mostly data driven. Data from somebody else in a big guide, big telescope, big project. If it is not guided by a single person for research, that can still be amateur astronomy, but not citizen science research. Because research has to be guided by somebody, designed in a way that it can contribute to a paper writing. Okay.
Thank you, sir.
I hope you got the clarity on your question. Also, I would like to take in continuation of the same question, the person who asked about the observatory. Sir, I am actually interested in spectroscopic analysis with the help of Fortran and Python. If you can recommend some good sources to learn data analysis and application in astrophysics, it will be good.
What's your name?
Can you please type your name because I think your user ID name is Supernova Inheritor, so you can write your
Is
name.
this a YouTube question?
It's coming from YouTube. Yeah.
If you are so interested, why are you hiding yourself?
Shivam Sharma. His name is Shivam
Okay,
Sharma.
so directly write to me. There are small observatories in India who are doing spectroscopy. Okay, I am myself do not have a small observatory and I do not do spectroscopy in optical band. So I can direct into those kind of people unless they have conflict of interest. You can certainly interact with them and grow your data analysis, own observatory, own telescope, etc. etc. So did not hide yourself. You directly talk to people. That will help you. If I do not help, somebody else will help you. I know a couple of people who are doing spectroscopy with small telescopes, and they are useful as an educational system. I am myself are interested in collaborating with them. Okay, so need not be in YouTube. You directly write to people, and it is not easy, not so difficult to find out our email addresses, right?
So now we'll take Mahi. Hello, sir. This is Mahi from Tamil Nadu. How do I become a part of the RAD at Home collaboration?
So simply search in Google, Facebook group if necessary to join. Okay, Reddit.com. If you go to our website also, first thing you will see the how to join. It starts with a Facebook group discussion. If you do not have a Facebook account or do not want to use Facebook, write to me, Reddit.com India, whatever address you find, my address or Reddit.com address. Write an email. will think how to include people like you. Okay. Yes,
So
let's
I've
begin
posted
again.
email ID of Nehru Planetarium and also Sir's email ID
Yeah,
in
right.
case you need any kind of assistance in like giving you the email addresses and all. You can definitely write to the planetarium or to one of the sir, and simply you can just Google it for further information. You will get the platform. Harshvardhan again, sir, on the topic of astronomical imaging, for example, in the case of event like EHT, knowledge about servers, networking, etc., are needed for such team efforts. So, where can learn these fields?
See, I first wonder what is your educational level. It depends upon what kind of training you have. Suppose you have training in engineering or technology, you will be useful more in the server networking, that kind of thing. Suppose you are more used to the general relativity, coding, and programming, that kind of thing. You will still be useful in the writing algorithm to image them better. So it is up to your domain expertise that you will be useful. Similarly, suppose you are very good at engineering, that only engineering, then you can still be useful in improving their telescope. They don't have a one telescope, they have dozens of telescopes in different parts of the world. Indian astronomers are not part of it from Indian institution, but you can finish your study or go to those places and join them, join their team. You cannot just sit at home, I want to be learn everything. It is not possible because you need to complete some course so that you can join formally that group. Either you go do MS there or you go your PhD there. That is how you will be joining. Suppose you go to those universities who are part of EHT, you can choose to select the professor that who is working on EHT. I want to join you, and they will employ you to do pure physics or do instrumentation or do data analysis. It's up to your skill. You have to join formally.
So I think
Yes,
he's from the BTech engineering. Yeah, he finished his BTech engineering physics, but I'm interested in science side rather than engineering side.
that's absolutely fine. Do not dislike your engineering. There are great radio astronomers who are engineer by training. Then they switch to physics PhD. So you have a great scope in the direction of radio astronomy or any kind of astronomy instrumentation related thing. So try for a MS or PhD in those bands. If you are sure about radio astronomy, RRI and NCRA will be radio engineering they will be doing. They are happy to take MSc as well as BTech or BE students. And if you are serious about PhD, I don't think people in India are working seriously on that band. We are not part of that collaboration as far as I know. But you have to go to those countries where the universities are part of PhD. Try applying for MS there, try applying for PhD there.
So I think most of the question we already done. Thank you for the
Thank you.
amazing
You're welcome.
questions. And actually, he's a science communicator. His stage name, although thank you for much for the
What's
answer.
your real name?
So his name is Shivam.
Okay.
Wanted to open the observatory in Uttarakhand. So we really congratulate you if you get the right connects, and we really hope something good happens in Uttarakhand in the future. I think with this note, I
Let
think
me
with,
know.
yeah, definitely it can happen. Only you just need a right people and write to the right people to get the things done. We'll wrap today's session, and tomorrow on the same time we'll further continue the discussion with Dr. Anand Hota. Meanwhile, if anyone left who wanted to join for the further more discussion during the boot camp, please write to the Nehru Planetarium at gmail.com or planetarium program at gmail.com so that we can add you for the further updates. So, wrapping today's session, again, once again, thank you, sir, for your time and all
Thank you.
the detailed things we have discussed during the session. And we're looking forward for the tomorrow's session as well.
Thank you very much. See you tomorrow.
Thank you.
Okay.
Thank you,
We'll
sir.
write something to the participants.
Yeah,
Like
thank you,
going.
sir.